Hi everyone, this is Mrs. J, and today we are going to talk about arithmetic sequences and series, but first please pause the video and give this warm-up a try. All right, go ahead and check your work here. So here's the sequences listed out, and then maybe you notice the pattern. So for the first one, you're adding 1 to get each consecutive term. For the second one, you add 3 to get each consecutive term, and then for the third one, you're subtracting 2. Now, maybe you notice those patterns, but look at the rule and look at the pattern. Maybe you also notice that whatever you're adding to get each consecutive term is actually the coefficient of n. So the first one, the coefficient is 1. The second one, the coefficient is positive 3. And the third one, the coefficient is negative 2. Now that is not a coincidence. It's part of one of the rules for arithmetic sequences that we're going to talk about today. And if you haven't already guessed, these are what we would call arithmetic sequences. All right, so what exactly is an arithmetic sequence? Like you saw in the warm-up, an arithmetic sequence is a sequence with what we call a common difference. This is a phrase I want you to be able to use when you're justifying your work. It has a common difference. That simply means that you are adding or subtracting the same value to get to the consecutive term. So here's a couple examples. 1, 2, 3, 4, 5. You're adding 1 to get to the next term. 12, 7, 2, negative 3, negative 8. You're subtracting 5 to get to the next term. So for the first one, the common difference is 1. For the second one, the common difference is negative 5. Here's some non-examples. 2, 4, 8, 16, 32. Now there is a pattern here. We're multiplying by 2 to get each consecutive term, but that is not an arithmetic sequence. That's a different type of sequence. Here we're adding 3, and then we're adding 5, and then we're adding 7, then we're adding 9. There's definite pattern to that, but again, we wouldn't consider this an arithmetic sequence. So arithmetic sequence, you must have a common difference. So now we're going to learn how to write those rules when we recognize that something is an arithmetic sequence. So this is a formula that you are going to need to know, and it helps us describe the nth term of an arithmetic sequence. So a sub n equals a sub 1, which means the first term, as you can see right here, plus n minus 1 times d, which is our common difference. So you can see for this, if you know the first term and the common difference, you can make the rule pretty easily. You're simply going to plug those things into our little formula. So for example, here you can see that if they give us a first term of 3 and a common difference of 2, we would simply plug that in for a sub 1 and 2. And then we will typically distribute and combine like terms to make our final rule look like a linear equation. So we won't leave our final answer like this. Again, we'll distribute and then combine like terms. All right, let's give it a try. Let's write the rule for the nth term of each sequence. So first, we do need to make sure that it is an arithmetic sequence because we don't want to use the formula for an arithmetic sequence if it's not arithmetic. So let's check for that common difference. From 3 to 8, I see plus 5, plus 5, plus 5. Okay, so we see that our common difference is 5, and we are given the first term, which is 3. So I'm simply going to substitute those things into this formula. I'd recommend writing the formula as many times as you possibly can. 3 plus n minus 1 times 5. And now all I need to do is distribute. So I have 5n minus 5, and then I'm just going to combine like terms. So 5n minus 2. So now that we have the rule for the nth term, you'll notice there's a second piece to this direction. Find a sub 15. Now when I see the phrase a sub 15, what this means is the 15th term, or the term when n is 15. And remember that n is the relative position in our sequence. So that's why it's really nice to be able to make a rule. Yeah, we could probably list out the sequence until we get to the 15th term. That probably wouldn't take us too long, right? But what if I asked you to find the 200th term? You would definitely not want to continue your sequence until the 200th term. So if you can make a rule, you can find whatever term you want. So if I want to find the 15th term, I'm simply replacing n with 15 in my formula. So I have 5 times 15 minus 2, which gives me 73. Now let's look at this second example. Let's again check to make sure that we do in fact have a common difference here. So here to here is minus 8, minus 8, minus 8. Okay, so we do have a common difference of negative 8. We can see that the first term is 55, so now we can make our rule. So again, I'm always going to start by writing the formula, and then I'm going to substitute for a sub 1 and for d, and then we can distribute. So it's actually going to be minus 8n plus 8. So we have negative 8n plus 63. All right, now let's use that to find the 15th term, or a sub 15. So negative 8 times 15 plus 63, and that gives us negative 57. So there you go. So just remember, it's super useful to be able to create a rule for a sequence, so then we can use that rule to find terms farther along in our sequence. All right, I have 2 for you to try on your own, so please pause the video and give them a shot. All right, go ahead and check your work here. So for the first one, the first term is 7, the common difference is 3, giving you this rule, and this is your 15th term. For the second one, the common difference is negative 7, first term is 15. So here's your rule for the sequence, and here is your 15th term. All right, let's try another one together. So here we are told that one term of an arithmetic sequence is a sub 19 equals negative 45. So that's telling us that the 19th term is negative 45. And they tell us the common difference is negative 3. We're going to write a rule for the nth term, and then we're going to graph the first 6 terms of the sequence. So if you look back at our formula, we need 2 things. We need the common difference, which they tell us, but we also need the first term. So we're going to have to find this in order to make the rule. So we can temporarily substitute this information they gave us to help us solve for a sub 1. So when they tell us this, what it means is when n is 19, a sub n is negative 45. So I can substitute that in. Again, since it's the 19th term, n is 19. And then I know that d is negative 3. So now I can solve for a sub 1. So we have negative 45 equals a sub 1 minus 54. So a sub 1 equals 9. So now I have that second piece of information that we need. And now I can make the rule for the nth term. So a sub n equals a sub 1, which is 9, plus n minus 1 times negative 3. And then we're just going to distribute and combine like terms. So do minus 3n plus 3. So a sub n is negative 3n plus 12. And then they would like us to graph the first 6 terms. So when you're graphing the first 6 terms, you're literally creating a scatter plot. So we can make a little table of values here if it helps us. So we have n and a sub n, and we're going to plug in 1, 2, 3, 4, 5, and 6. Or once we know the first term, we can simply follow our pattern, which is subtracting 3. Or again, we can just use our explicit rule, which we wrote right here. So we know that the first term is 9, and then we have 6, 3, 0, -3, and -6. So these we're simply going to plot on our scatter plot. Just like an xy axis, except this is n, and this is a sub n. So we know a sub 1 is 9, a sub 2 is 6, a sub 3 is 3, a sub 4 is 0, a sub 5 is -3, and a sub 6 is -6. So you can see when we graph at the terms of an arithmetic sequence, they should always be in a straight line because there's a common difference, which AKA means slope. So there's a common slope. Now for this, we're not going to connect the dots because these are just those individual terms. The stuff in between does not exist for a sequence. It's just a list of ordered terms. So this is what our graph would look like. All right, go ahead and pause the video and see if you can try this one on your own. All right, go ahead and check your work here. So I substituted d equals 6 because that was given, and I temporarily substituted a sub 12 equals 52. So I replaced a sub n with 52, and I replaced n with 12, and that allowed me to solve for a sub 1, which was that missing piece of information that we need. Remember, we need the first term and the common difference to make our rule. And then I plugged in a sub 1 and my d value, and I got 6n minus 20. And then I found the first 6 terms here and plotted them to show that it makes that straight line, which we should expect for any arithmetic sequence. All right, so now we're going to try one that's a little bit trickier because we are not given the first term or the common difference, but we are given 2 terms of an arithmetic sequence. So a sub 7 is 17 and a sub 26 is 93. So we can actually use those to make a system of equations. And if we have 2 equations, we can solve for the 2 things we're missing, which is a sub 1 and d. Okay, so our first equation, we can use a sub 7 equals 17. So I'm going to temporarily substitute that. So I have 17 equals a sub 1 plus 7 minus 1 times d. And I can simplify this to be a sub 1 plus 6d. And then I can make a second equation using a sub 26 equals 93. So I have 93 equals a sub 1 plus 26 minus 1 times d. So 93 equals a sub 1 plus 25d. So now I have a system of 2 equations, which I can solve using either the elimination method or the substitution method. I'm going to do elimination. So I'm going to rewrite this equation right here. And I'm going to multiply both sides of this equation by -1 to create opposite coefficients here. So -17 equals negative a sub 1 minus 6d. And then from here, if I add vertically, you'll see that my a sub 1 term is going to eliminate, just leaving me with d. So I have 76 equals 19d. So then I can find that d is equal to 4. And then you can take that and you can actually substitute it into either of these. It doesn't matter which one. So maybe I'll substitute it into the one on the left because the numbers are a little smaller. And that will allow me to solve for a sub 1 plus 6 times 4. So 17 equals a sub 1 plus 24. So we can see that a sub 1 is negative 7. So now I have those two pieces of information that I need to make my rule. So a sub n equals a sub 1 plus n minus 1 times d. And now it's just distributing and combining like terms. So plus 4n minus 4. So I have 4n minus 11. And there you go. So these are definitely the trickier problems, again, because we don't have either piece of information that we would like to make our rule. We need a sub 1 and d. So that means we have to create a system of two equations to solve for those two things. We're going to do one more of these together, but I'm going to show you a different way to approach these. So rather than making a system of two equations to solve for this, I can take advantage of the fact that arithmetic sequences, as we saw when we plotted them, have a constant slope. So if the slope is constant, I can treat these two pieces of information like coordinates. So I have 771 as one, and then I would have 1626, and I can find the slope between them, and that will be the common difference. So that slope is the common difference. So I know how to find the slope between those two lines. I just do y2 minus y1 over x2 minus x1. So I have negative 45 over 9. So I see that m is negative 5, which again, that slope is the same as the common difference. So once you have the common difference, we still need to find a sub 1, but we don't have to create a system of two. We can just simply substitute one of the two pieces of information to help us find a sub 1. So maybe I will use a sub 7 equals 71. So this is like what we did 2 examples ago. So we have 71 equals a sub 1 plus 7 minus 1 times our common difference, which is negative 5. So 71 equals a sub 1 plus, here we have 6 times negative 5, so negative 30. So a sub 1 is 101. And then we can make our equation. So 101 plus n minus 1 times our common difference. And then we have a sub n equals 101 minus 5n plus 5. So a sub n equals negative 5n plus 106. And there you have it. So again, you can do it this way. So this is, we can use our slope formula to help us find the common difference. And then we still need to substitute one of the values to find a sub 1. Or you can do the process we did in example 3, and you can create a system of two equations to find a sub 1 and d. All right, at this time I'm going to ask you to pause the video and give this one a try on your own. All right, go ahead and check your work here. So I did it with the system of equations method. I replaced n with 5 and a sub n with negative 43. And here I replaced n with 12 and a sub n with negative 8. Here's my systems. I multiplied this equation by negative 1 and placed it here. And I solved for d. I substituted it into this equation to solve for a sub 1. And then I used those two terms to make my rule for this arithmetic sequence. All right, the last thing we're going to do today is learn how to find the sum of a finite arithmetic series. So remember, a series is when you take the numbers in a sequence and you add them up. So last video we learned how to do this by hand. We just listed out the numbers and we just added them up manually, which is fine unless you have a lot of terms. What if you were finding the sum of the first 200 terms? Luckily for arithmetic sequences, there is a formula that we can use to help us find the sum of the first n terms. And this formula, again, you'll need to memorize this formula to use it. It's n, which is the number of terms, times a sub 1 plus a sub n, so the first term and the last term, divided by 2. So all we need to do is find the first term, find the last term, and figure out how many terms we're finding the sum of, and then we plug in our numbers, and that will be our sum. All right, let's give this one a try. First, it is important to notice if the sequence inside our sigma notation is arithmetic. If it looks like a linear function, like y equals mx plus b, it is an arithmetic sequence. So this is telling us to find the sum of the first 20 terms of this sequence. So I'm going to write the formula again. So this is just our formula. So we have n over 2. Sometimes it's written like this, which is the same. It's just I'm pulling out the 2 instead of putting it in here. So this is how I usually will write that formula. So let's write the information we know. Since the top number is 20, that means I'm finding the sum of the first 20 terms. So n is 20. Well, let's see if we can find a sub 1 and a sub 20 to plug in. So a sub 1, I'm just going to plug in 1 into our rule. So I see that a sub 1 is 10. And then I need to know a sub n, which in this case is a sub 20. So 3 times 20 plus 7. So our last term of this in our series is going to be 67, or our 20th term. So from here, I'm just going to plug in those numbers. So the sum of the first 20 terms is 20 divided by 2 times the sum of 10 and 67. So the sum of the first 20 terms is 10 times 77, which is 770. So again, an alternative to this would be literally listing out the first 20 terms and then adding those up manually. So this is definitely a case where memorizing this formula is going to be super, super useful. All right, here's the last you try, so please pause the video and give it a shot. All right, go ahead and check your work here. You can see that I'm finding the sum of the first through 18th terms, so n is 18. I plugged in 1 into my rule right here to find my first term, and then I plugged 18 into my rule to find my last term, or the 18th term, and then I just plugged those into this formula to get a sum of 990. All right, that is all for today's video. Thank you so much for watching.